To find the dimension of given expression or given quantities in the given expression, here are some basic examples. The first one, v equal to at plus bt square. T is for time, v velocity. You see, at will have the same dimension as velocity, that is lt minus 1. So, dimension of A is going to be lt minus 1 upon this time, that is t, it becomes lt minus 2, the dimension of A. Because this very term has been added with this one, both will have the same dimension. So, dimension of bt square will be equal to that of velocity, or this one, and velocity is lt minus 1. We are writing this whole thing in terms of dimension. That's why the dimension of b is going to be lt minus 1 upon t. This is a square. It becomes lt minus 3. The dimension of A and B we got for this relation, the first one, V equal to AT plus BT square. Similarly, the third relation that we have is P equal to P naught E minus alpha T square. Terms are usual. P pressure, T is time, and alpha we have to find. You see, this is power, exponent. For power, it is allowed to be the number only. Means you can never say x to the power 2 minute. That's meaningless. It's going to be only x power 2. Similarly, it is understood that this very expression alpha t square, it will have no dimension. Means m0, l0, t0. It is dimensionless, it's a pure number. So, in order to find the dimension of alpha, it's going to be t0 upon this t square. It becomes t to the power minus 2 alpha. And suppose you want to find the dimension of p naught, because this whole thing would be a simple number, it's a numerical value only. P0 will have the dimension of p. Then the second expression that we have is back to van der Waals equation, that is P plus E upon V square, V minus B, that is equal to RT. The dimension of B, that is equal to dimension of volume, because we have taken the difference, and principle of homogeneity says addition, subtraction, equation or comparison is possible between the quantities having same dimension. So, inference of the principle is that both will have the same dimension, and dimension of volume you know is L cube, it's going to be L cube, that for B. Similarly, dimension of E upon V square, it will be dimension of P, that is pressure, and you know pressure has the dimension ml minus 1 T minus 2. That's why the dimension of A will be equal to V square will get multiplied over here, that is L cube and square L6. The whole thing becomes ml to the power 5 T to the power minus 2. This is the dimension of A, which is in fact van der Waals constant. Now, the dimension is basically used for two important purposes. One is to check the equation, correctness of the equation, and the second is to establish the relation. Here, we have considered one example for establishing the relation. You are given the information that time period of a pendulum depends on its length, the acceleration due to gravity, and the mass as well. The dependence of time period is given for these terms, but the powers are not given, powers are unknown. You have to suppose the powers from your side. just take the dimension both the sides. You see, it's a simple time. It is going to have the dimension t only. And this side, it is L to the power a, g, LT minus 2 to the power b, m to the power c. Overall, it becomes MCL A plus B and T minus 2B. That side is only T. So, if you compare the powers of similar quantities, this side is 0 for M and this side is C. C becomes 0. That means mass will disappear from the relation. It's having no dependence on mass. You see, time minus 2b is the power here. This is 1. B becomes equal to minus 1 by 2. This is 1. You got the value of B also. What remains is A plus B. For L, that side is 0. A becomes, this is 0. A becomes equal to minus B and that is plus 1 by 2. You got the values of A, B and C, the unknown powers that we assumed initially for lengths G and M. That is the method how we proceed for establishing the relation. Now in the last we'll point out some limitations of dimensional method. This method is true for quantities having dimension, because it's not going to help for establishing the relation between dimensionless quantities. Dimension, in fact, doesn't differentiate between dimensionally similar quantity. For example, I tell you a strain that has no dimension and refractive index that has no dimension. From dimensional point of view, strain and refractive index both will be similar quantities. So, underlying idea is that dimensional method is not going to discriminate between dimensionless quantities.